So today is going to talk to us or teach us about structural equation modeling with Lavaan and other open tools. So without further ado, take it away, Michael.
Well, thank you very much. Uh, Slight correction with the bio now, as of about a week ago. I guess it's not probably not effective till July 1st, but associate professor now. Uh,
Oh, congratulations.
so
Excellent.
congratulations to me. Yeah.
Yes, excellent.
Let's see. So today we're talking about structural equation modeling. Uh, I'm sort of approaching this like I would approach a lot of classes that I would have on this, which means that you get the normal things that I start off these classes with is a dog picture and a joke. So I think if I stop sharing that and I go to here, you can get requisite dog picture. So this is Jamie. He is sleeping in a University of Michigan sweater, which is my wife's alma mater, and on top of the couch, on top of a pillow. So the tough life that he leads for that. For your statistical joke with this, so x squared and x cubed were sitting around talking to each other the way that functions of x typically do. X squared asks x cubed, say, are you particularly religious, x cubed? And X Cube says, well, I believe there are higher powers than us, if that's what you mean. That's about as good as the jokes get. Many more of those to come. Okay, without further ado, we're going to get into this workshop topics of the day. The things that I want you to leave with for this talk is really just more so than like example scripts to fit a bunch of structural equation models. I want you to leave with a sense of what a structural equation model is and how to build the model that you want to build. There are a lot of ways, there are a ton of resources out there to do example scripts on any model that you could ever want. You can put it into ChatGPT or Claude or other AI instruments and have it spit out a script that will do a model that you ask it to do. But there isn't a way to get you to understand what that model means, from AI. So it will do some explanation. It might be right, it might be wrong. But the goal here is not to give you a bunch of scripts and to have you, here are 30 scripts for different models and let's go over them. The goal is really to talk about the sense of what a structural equation model is and to have you leaving with a sense of that and to give you some sort of hands-on practice in building extremely simple sort of toy parts of structural equation models that might be a little bit unconventional. So we're going to talk about what an SEM is. We'll do some pictures and some make a big point of going back and forth between these three different forms of specifying a structural equation model. One of them is really in code. One of them is really in a diagram, and another of those is really in a set of matrices. And there's a one-to-one correspondence between this code that you make, this diagram that you make, and the matrices that you make. And you can go back and forth between all of those things. We'll talk a little bit about Lavaan and Lavaan's kind of deal, what its sort of overall design philosophy is in making these models. We'll have, I'm slotting this to have a fair amount of time to actually have everyone here live go through and do some things. If we need to go into breakout rooms, we can, but I want you to sort of be following along and be able to like actively do some of this stuff, and we'll have time to like really do some exercises in here. We'll wrap up with sort of like a cheat sheet about some of this stuff and advice for fitting some more realistic models as we go forward. Okay. So what is a structural equation model? You can say, well, it's a model of structural equations in the way that definition sort of lends you to that. But I want to sort of roll back in our notion of what a structural equation model is and talk about just what is a model? What do we mean by a model? Some of you might know this sort of very often quoted statement from George E.P. Box, all models are wrong, some are useful. You might not know that George Box has a little bit of a relation to another famous statistician. He's in some ways related to, well, not genetically related to this other guy. If anyone knows who this is, you get double points on your workshop attendance. I'll like pause a second for chat here. It's easy time to chat. Does anyone know who the person on the right is? The person on the left is George E.P. Box. The person on the right, see any guesses in the chat? Oh, there's a guess in the chat. Fisher, Terry Muffin, Murphy, sorry. Absolutely correct. This is Ronnie Fisher, Sir Ronald Fisher, actually. He's knighted. Sir Ronald Fisher, if you've ever used ANOVA, you have Ronald Fisher to thank for it. If you've ever, let's see, used maximum likelihood to fit a model, you have Ronald Fisher to thank for that. If you've ever used randomization to balance errors or try and make stronger causal inference in an experiment, Ronald Fisher you have to thank for that, among many, many, many other contributions. Ronald Fisher's daughter was Joan Fisher. Joan Fisher was married to George E.P. Box. So George E.P. Box's father-in-law was Ronald Fisher. How would you like that Thanksgiving dinner for yourself? Okay. A little bit about models. So a model is a description of reality, and we know that it's an incorrect description of reality. Thing is, we know that it's incorrect, and we are intending it to be incorrect. A model is not just wrong on accident, it's wrong on purpose. It's wrong in specific ways. So you could imagine making a map of State College. If you wanted this map to be absolutely accurate in every detail in every way, it would take up the exact same amount of space as State College itself. It would have to have all the things and all the critters and all the facets of State College. The map would be the size of State College, which is not so useful to actually have. In a slightly reduced form, you can think about a subway map. So this is a subway map here on the right. A subway map is purposefully wrong. Do you imagine in your wildest dreams that any subway is exactly as straight as this green line is portraying this subway line to be? I'm sure it takes some turns in there. I'm 100% certain that that green line in the subway is not straight. I'm also absolutely certain that the distance between, let's say, Royal York and Old Mill is not the same as Islington and Royal York. Although it looks that way on this map. This map is wrong, and we know that it's wrong, but it's still useful. By the same token, what we're trying to do when we're making structural equation models is make models that are wrong, but that are useful for our purposes. They're useful descriptions of reality, not in spite of being wrong, but in part because of the ways that they're wrong and because of the ways that we know them to be wrong. Pablo Picasso has this quote about art, that art is a lie that tells the truth. Well, I would modify this to say that a model is a lie that tells the truth. A model is a way of saying something wrong that in a deeper sense, in a broader sense, is also saying something that is true. We can similarly try and understand more specifically about structural equation models by referring to the various names of structural equation
Michael?
modeling programs. Yes.
Sorry, I'm going to interrupt. There's a request actually.
Sure, absolutely.
Whether because I think you're sharing your desktop.
Yes.
Because of that, the way that we see is like we see you in half of the screen and the slides in the other half. So if you're looking at a laptop, I think these slides are tiny little. So
Let's see if I can adjust this a little bit.
yes,
I can put me in here and make me sort of small in the corner.
you might have to reshare the screen though, I think. I don't know.
I'm working on it. So
Oh, that
I think I
works
should
perfect.
appear tiny in the lower right-hand corner near
Yes.
what used to be the Penn State logo now.
Yes. Yes, that works. Thank you.
Better. Okay. Happy to do it. Okay. So we can try and understand structural equation models based on the names of computer programs that have been used to fit structural equation models. The oldest, the granddaddy of them all, is called Literal. It's for linear structural relations. That's what Literal stood for. There was another program called structural equation modeling. It's the SEM program. Another program was called covariant structure analysis. This was COSAN. It was part of the facilities that ran in SAS. Let's see, some other people made a program that was called latent variable analysis with dichotomous ordered categorical and continuous indicators, which went by the name LACI. You can imagine the graduate student that created LACI and what his feelings were on his tasks. Linear structural components is another name for some software that went with this. That software eventually became, actually LACI and LizComp eventually became M+, if you're familiar with that. Linear equations, so EQS was based on linear equations. The sort of strange name of a reticular action model gets its name actually from an unconventional use of the word reticular to mean network, that it was really supposed to be a network action model, that a reticular model was one that had this sort of web of interconnected variables together. The program that we're going to be talking about today, for the most part, is called latent variable analysis. That's what Lavaan stands for, the LAVAAN in there. And a program that I've worked on has been OpenMX, which is the kind of descendant of MX, which was for matrix expressions. So in these names, you see some commonalities. You see linear pop up several times in linear structure, in Lizroll and LizComp and EQS. You see latent variables show up in a number of names here. You talk about this structural part where you have this sort of idea of a structure, or maybe a network or a mapping of different kinds of things together. And you see matrices come up. And all this sort of is evocative of what we mean by a structural equation model. To continue in this same vein of being evocative of what exactly a structural equation model is, I was teaching a structural equation modeling class, and I asked the students after a few weeks in the class to tell me what a structural equation model was, to try to assess what their notion of what they were doing in this class was. So here are some definitions that they gave on what a structural equation model is. It's a network of linear regressions with both observed and latent variables. We're going to see a lot of themes of this come up across these names as well. Another student said, a model that represents the relationship between multiple variables, both latent and observed, through related regressions. So regression sort of comes up again in this definition. And then now, a network of regressions among latent and observed variables. This is one's nice and brief. And again, regression kind of rears its head in this definition. A model that explains the relationship between variables, whether latent or observed, using a covariance matrix. This is one of the first times so far that covariance matrices have popped up in the definition here. Those will be important, as we'll see. A regression model for latent and observed variables. Nice, simple, to the point definition there. A method of modeling the means, variances, and covariances of latent and observed variables. So again, covariance comes up. So linear models come up with linear regression, latent variables, observed variables. These things are sort of evoking in the same general space of terms that we're thinking about. I'll sort of glance through a couple more of these as we go on. So framework for variances, covariance is a means, set of equations. Now we have equations coming in, explaining the path diagram between latent and observed variables, using latent and observed variables to simplify the world and its patterns of data. That one's sort of a nice change of pace. A compact way of doing many related regression models, or a model with structured relations between latent and observed variables based on reparameterizing the covariance matrix. Hopefully this is sort of giving you the sense of, in general, what we're doing with structural equation modeling, that there's some key components to this definition across all of these. So one of them is a distinction between a latent and observed variable. Sometimes latent variables are also called hidden variables, and sometimes observed variables are also called manifest variables. I'll use these terms sort of interchangeably. The key distinction between a latent and an observed variable is one of them is a column in your data set. An observed or a manifest variable is a column in your data set. Any other variable that you have is latent. We might also call a latent variable sometimes by another name, factor. So it's a latent factor or just a factor, or maybe a construct to refer to those latent variables. And in general, what we're doing with the structural equation modeling is we're mapping relations between observed and latent variables. I'll put forth my own definition of what a structural equation model is. It's a systematic way of representing the joint distribution of a set of possibly latent variables in terms of structurally related free parameters that correspond to a set of graphing and diagramming rules. So I like all these definitions from the students, but if I were to give a definition of what a structural equation model is, this is the definition that I would give. But there are key components to this that you might have latent and observed variables. You're making a model for the joint distribution of a whole bunch of variables, not just one variable at a time. It's intrinsically a multivariate way of modeling things. You have multiple variables and you want to know how they all relate to each other. And you have a lot of flexibility in how you determine what those relationships are. So if you go back to other kinds of techniques, if you go back to t-tests, regression, ANOVA, multiple regression, you have a lot of restriction about what kind of relationships are possible in those sorts of simpler models. There are many fewer restrictions in what kind of relations are possible in structural equation models. But the way that we make them corresponds to these diagrams. If there's something that people have seen who haven't done structural equation modeling before, they've probably seen diagrams of structural equation models. You might have used those sort of statistical techniques, but you've seen these pictures. And there's some kind of mapping between these pictures and the math behind them. That's one of the things we're going to be talking about next. So when we make a structural equation model, a key thing that we do is we make a diagram for it. The diagram follow a number of conventions or rules. Here are the ones that I'll be presenting today. So the first one is that a circle, or sometimes an ellipse, refers to a latent variable or a factor. A square, or sometimes a rectangle, will refer to an observed or manifest variable. And the slightly less conventional part is this triangle refers to a constant or means in a model. Then you have one-headed arrows that make regressions. And you might have different kinds of regressions depending on the model that you're making. You might have regressions between observed variables. You might have regressions between latent variables in the second one. Or you might have a regression from a latent variable to an observed variable. It is technically possible to have a regression from an observed variable to a latent variable in that reverse direction, but we typically don't do that for a number of reasons outside of a few very specialized cases. And when we do, there's sort of technical requirements about what that really needs to entail. But these ones that I'm showing here, regressions among manifest variables, regressions among latent variables, and a regression from a latent variable to an observed variable are very common. We'll see those all the time. In the special case of this last one, when we have a regression from a latent variable to an observed variable, we're going to call that regression a factor loading. It is exactly a regression involving a latent variable predictor and an observed variable outcome, but we're going to call it a factor loading sometimes. It's identical to what we do in factor analysis. So the other kinds of paths that we'll have are two-headed paths. We can have two-headed paths between observed variables, between latent variables, and we can also have a two-headed path from a variable to itself. In general, two-headed paths refer to bidirectional relationships, kind of undirected relationships. It's not one variable predicting another. It's just that two variables go together, they covary in some way. And a covariance of a model of a variable with itself is a variance. A covariance of a variable with itself is a variance. So we see covariance between x and y, f and g, and then we have the variance of g and the variance of x here. Last part in here is means, that we can have means on each of these variables. So we can have a mean of x, we can have the mean of the latent variable g, we can have a mean of this variable with its variance in there. And this is sort of starting to transition to the next part where we start to get more interesting diagrams where we can have multiple paths on diagrams. The key thing that we would like to do with our models is we're going to have multiple paths on them. So I'm keeping our sort of legend up at the top to remember which variables are latent, manifest, or constant. Here I'm drawing a single triangle. I've got three different observed variables, one latent variable. We're not going to worry yet if you could actually fit this model. You cannot actually fit this model. It's what's called not identified. But you can draw the diagram. You could try and put this into an SEM program and try and get it to run. It'll throw warnings and errors and complain to you about not being possible to do this. But it is possible to draw the diagram. It's possible to write out equations for it. It's possible to write code that goes with this model. So here, I'm also showing how this diagram sort of maps to a set of equations. So this triangle is the constant value 1. X here is an observed variable outcome. The outcomes go on the left-hand side of an equation. The predictors go on the right-hand side of an equation, just like you would in regular old regression. There's a coefficient that can go on this path between the constant 1 and the observed variable X. The parameter there is labeled A. A lot of times you just won't put a label on it as a convention, but here I have. So what this first equation is saying is X is equal to A times 1. So X is an observed variable. We're saying this observed variable, according to our model, is the constant value A multiplied by 1. But in the first two, I've kind of write that out explicitly, but usually you don't have to write out multiplication by 1 because it's the multiplicative identity and it's the same as doing nothing at all. So this model is saying that X is a constant value A, Y is a constant value B, Z is a constant value C, and this latent variable G is also a constant value D. This is not the most interesting model. It's saying all the variables in my data are constants. I could assess that and see how well it fits or does not fit. But right now it's saying all my variables in my data set are just constants. The key reason for showing this diagram is I've added a path now. I've added a path from my latent variable G to my observed variable Z, and I've labeled that F. And how this shows up in the equation is now Z has two pieces to it. Z has a piece C that comes from this constant, and it has this piece F and G that comes from that latent variable. When you take this latent variable G, you multiply it by the path coefficient there, and then it results in Z, which is the same idea as just regression, but we might not be used to seeing it drawn out like this. Other key thing to note is when you have two arrows going into a variable, those paths that go into that variable get added together. So we have this one path that comes from this constant C, and we have this other path that comes from this latent variable G, and we add C plus F, and F gets multiplied by the latent variable G. So when we have multiple paths going into the same variable, those paths get added up. Another thing to think about here, another example just to get us thinking of very simple examples of structural equation models. Here we've got 4 observed variables. I have no latent variables. And W is a predictor of all of them. So W predicts X, W predicts Y, W predicts Z. What that shows up on when we turn that into a set of equations is we have 3 different outcomes, but one and the same predictor for all of those outcomes. We have 1 predictor, 3 outcomes. We can turn that around and have 1 outcome and 3 predictors. When we have, again, multiple predictors, the effects get added up together. So at this point, we sort of have very basic building blocks, very basic ideas of what you can do with a structural equation model.
Michael,
Uh,
can I ask a quick question?
Absolutely, yeah.
In the previous slide. So
This
because
one here?
W, yeah, so
Yeah.
because W is the outcome variable, do you have to switch? I mean, I understand that in terms of the equation, it doesn't make any difference, but do you have to switch the two sides of the set of variables or not? It doesn't really matter.
So you're wondering if it would be possible to write ax plus by plus zz equals w.
Uh,
Is that correct?
no. So in your previous cases,
Yeah.
the I might have I don't know
Oh,
whether I switched it in my head.
oh,
So
you're wondering
so
about
here,
how I've lined
yeah.
up the.
I mean, I
I see.
understand the
I see.
directions
I
of
see.
the arrows
I
and
yeah
everything is
yeah.
okay.
Okay. This is an important thing to note as well. The diagrams do not care where you put the variables.
Got it.
Arrows don't need to go to the left. They don't need to go to the right. They don't need to go up. They don't need to go down. They could go in all different directions. The diagram is the key thing that matters with the diagram uh, is what variables are connected to what other variables.
Got
It
it.
does
Yep.
not matter where you put them. The key thing is what direction the arrows go. If they go one A to B or B or W to X or X to W, or if it's two-headed or if it goes to itself, it matters what's connected to what. So that's that network aspect here. It does not matter where you put any of those variables. We try to make them look aesthetically pleasing. And there are a number of ways to be systematic about how you make something that sort of looks nice and sort of makes sense. But it's the same model no matter where you put the variables, no matter how the diagram looks. The You can spread things out or flip them upside down or whatever. As long as the same things are connected to one another, it's the same model.
Thank you.
The last thing I'll say about this is the sort of mathematical term for that is we don't care about the diagram's geometry, we care about its topology. Okay, so in this equation, so now we're doing multiple paths. We can have W as an outcome, multiple predictors on our outcome variable. We could put it on the left. We could put in our diagram, we could make this any old way we want. We can arrange it any old way we want. In the equations, by convention, outcomes go on the left and all the predictors and everything go on the right side of that equation. So we've started showing sets of equations that go with our diagrams. Uh, but I've explicitly, in the previous diagrams to this, excluded any two-headed arrows from any of these diagrams because the two-headed arrows typically don't go into equations. Two-headed arrows are an important part of the model. They go into matrices that represent the model, but we don't have typically equations that represent any of those two-headed arrows. So the two diagrams that I've shown here, sort of top and bottom, are representing the same exact process. This is another thing that we'll encounter a little bit with structural equation models, that diagrams can look kind of different even though they're representing the same model. So here I have F predicting G. F and G and H are all latent variables. F predicts G. G and H covary with each other, and everything has variances. So F and G and H all have variances. G is predicted by F with a coefficient value R here. And that is exactly equivalent to this equation that I've written, that G is equal to R times F. Now I'm adding plus E. The plus E is a little bit hard to think about when you diagram it the way it's diagrammed on the top. But when you diagram it the way it's diagrammed on the bottom, it starts to make a little bit more sense. You can imagine this residual value E is also a latent variable, that the residual value is also a latent variable. Just for the sake of having it fit in this diagram will sometimes draw the residual latent variables smaller. It's still the same, it's a latent variable, even though we've made it smaller. We're making it smaller just so it sort of conceptually fits nicely. It's the same kind of latent variable as G is a latent variable. We've just made it sort of pretty for our purposes. So if you think about it in this bottom diagram, then you have G is an outcome of F times R plus E, where E is this other latent variable. And then E correlates with this other latent variable D, which then predicts H. But then E has this variance associated with it that I'm calling VE. One of the things that I haven't drawn in here, but is sort of implicit in this translation between this diagram and this equation, is that the coefficient on this path that goes from E to G is 1. So that coefficient that goes from this little residual to this latent variable, it must be 1 if it's going to correspond with this diagram over here. This is a common convention in many, but not all, structural equation modeling diagrams, that sometimes unlabeled paths will be estimated, sometimes unlabeled paths will be fixed to a value like 1. One of the joys of figuring out, translating a structural equation modeling diagram from a paper into your own actual model is figuring out which values, what conventions that they're using, what values need to be fixed, what values can actually be estimated. All the diagrams I've shown so far are like little toy diagrams that aren't really meant to be taken too seriously, but just to give you a sense of what these diagrams can start to look like. For some real examples from the field, I've got a few of those. And then I think before we get into the design of Lavaan, I'll pause for questions, but I'll sort of show these examples beforehand. This is what's called an ACE model, an ACE model for additive genetics, common environments, and unique environments. This is a model that's common in behavior genetics. The goal of a model like this is if you have two observed variables, let's say it's the same outcome variable you've measured on two members of a twin pair. Let's say you've got a twin pair, you've both measured height on both members of a twin pair, and you want to see to what extent height is closely related to additive genetic factors or maybe common environmental factors or unique environmental factors. So a model like this sort of decomposes those sources of variance. Without going into details, we'll sort of leave it with that example. This is another example. This is what I would call a longitudinal factor model. Here you've got the same three variables measured at 2 time points. At time point 1, you've measured XYZ. At time point 2, you've also measured XYZ. You think there's a factor, a latent variable that underlies all your observed variables at time 1. And the same latent variable underlies those observed variables at time 2, and there's regression over time from the factor that goes from time 1 to time 2. Getting a little bit crazier here, this is what's called a dual latent change score model. This is, again, a longitudinal model for a single variable that's measured, in this case, 4 times, measured at time 1, 2, 3, and 4. That's what y is. And you've got all these other latent variables and all these other things sort of built around it to make a model of how this variable changes over time. You can get real crazy with this sort of model and go what's called a bivariate dual latent change score model. So now you've got y measured at 4 times, you've got x measured at 4 times. You basically have a dual latent change scored model for one and for the other, and then you've got a relationship between them. Models like, so I'm showing a model like this to show you how complicated and crazy structural equation models can get, even though the ones that we're showing today are really, really simple, really toy things that you can just sort of tease out together in just a couple of minutes. They can get very involved, very intense with a lot of moving parts and a lot of complicated factors to them. Okay. So the next thing I wanted to get into is kind of a design of Lavaan, but I sort of want to pause here for a minute in case there are any questions about material that we've discussed or covered so far.
I have two questions. Can you hear me?
Sure,
The first question
absolutely.
is, I was wondering, could you explain more about the arrow pointing to itself? So whether conceptually we can understand why, for example, the y1 or y2, there's arrow point to itself. And my second question is, why sometimes the triangle, the constant is included, but sometimes it's excluded. So
Yeah.
they're like, thank you.
So by arrow pointing to itself, could you elaborate a little bit what you mean by that?
Yes. Oh,
Oh, I'm
and
asking you, like, what do you mean by that question?
What does really capture? I know it's measure the variance within itself, but conceptually, how can I explain when the two arrow
Okay.
points at itself?
So you're referring to like this VE
Yes,
arrow where you've got a two-headed arrow that goes from a variable to itself.
yes.
Okay. Uh, so conceptually, it's really it's really instantiating that a covariance of a variable with itself is variance. That is the definition of what variance is. So, like, if you have this two-headed arrow between G and H,
Mhm.
that's clearly the covariance between G and H. That there's a bidirectional relationship between G and H. That is the covariance.
Yes.
So, if you wanted to model the covariance of G with G, then you'd have to have a two-headed arrow that goes from G and then back to G. So you sort of the only way to represent, a two direction that the direct analogy of covariance to variance means that you go from a two-headed arrow across two different variables to a two-headed arrow on the same variable.
Hmm.
There are a number of different conventions for this. So, for example, in this diagram here, I've got a two-headed arrow on a variable to itself for f, but here I have this other latent variable over here on the right that has also a two-headed arrow that goes to it, but it's not, we didn't put this two-headed arrow just directly on f. That's done to emphasize or sort of think about uh, this two-headed, this variance term over here as a residual variance,
Hmm.
because it's the variance in f after accounting for the variance that's sort of from this regression prediction of f at time 1 to f at time 2. There are some other ways of thinking about that. Sometimes you'll see diagrams that have a one-headed arrow without any variable that it's coming from. It's just a one-headed arrow from nowhere. I don't really like that convention, so I'm not showing it here, but it's one that you'll see out there in the world. Really, like the two-headed arrow, it's just the way that I think about it anyway, is uh, it's the direct definition of covariance of a variable with itself means variance. That's the math of what it means. I'm not sure that I've satisfactorily answered your question, but I think I'll leave it there for now.
Yes, very helpful. Thank you.
Okay. The second question that you asked was about the triangle and why it
Yes.
shows up sometimes and why it doesn't
Yeah.
show up sometimes. So, in the history of structural equation modeling, for the first, depending where you put a starting point, let's call it maybe 70 or 80 years of structural equation modeling, people did not model or care about modeling the means. There, in fact, was no way that you could model the means of your data for a long time. The way that so a lot of structural equation modeling has sort of developed with the idea that, like, yeah, we don't care about means. So in a diagram like I'm showing here for this longitudinal factor model, there's no triangle in it. There's no means anywhere in that diagram. Similarly, for this model in behavior genetics, this ACE model, there's no triangle in it. I haven't said anything about the means. A lot of times in a lot of structural equation models, we don't have interesting things to say about the means, so we don't even include them in the diagram. Another reason that we might not include them in the diagram is we might have some interesting things to say about them, but it makes the diagram too messy. So this is a problem that comes up again when you're looking at structural equation modeling diagrams out in the wild, is sometimes they won't put things in the model that are really there in the model because it gets too messy. I'll show an example of this. I'll sort of jump way ahead here. This is a full-ish diagram of a structural equation model. So here I've got two latent variables, f and g. I've got four observed variables, w, x, y, z. And this sort of like describes pretty much everything that I would put in a model. I haven't labeled all the paths or put values on them, and some of those paths I might need to fix to 0 or to 1 to get the model to actually run. But this is like a pretty full diagram. If I were to explain this diagram to a person casually, or even maybe in a paper, I might just draw this diagram.
Yeah, that makes sense. Yeah.
And people would say, like, yeah, like this is like, I'm basically talking about the same model here. Like you sort of get it, you sort of fill in the rest of the pieces in your mind about like, yeah, all those other things, like I get that they need to be there. They just sort of like, there's all this other stuff in the model when you actually have every little thing in the model that is supposed to be there. The model gets sort of messy. And most of the time, for a lot of purposes, we sort of get close enough to what you mean when you look at this shorthand diagram. That's great if you're familiar with the model and if your mind can fill in the details, or maybe if your software can fill in the details for you. But if you're not familiar with the model or your software doesn't fill in the details, it can be really maddening to try to be seeing diagrams like this and realize that you have to actually do all this other stuff in there to actually fit that model. So it's part of the learning curve of getting into structural equation modeling, is sort of accommodating this sort of shorthand that often goes with those models. Other
Thank you.
questions? Yeah, other questions? Okay. So without further ado, I'll sort of get into some of the details of Lavaan, which is a software program that we'll use in this workshop. Lavaan is the software program that you would develop if you were serious about the following things. So if you really wanted to fit conventional structural equation models really well, if you wanted it to be open source, if you had a high emphasis on making sure your scripts could be readable, that humans could sort of read them, glance at them, and sort of get the gist of what your model was. If you didn't want to do very much typing, if you wanted to estimate your model in R, if you wanted the model to be estimated pretty fast, if you wanted a pretty quick, easy learning curve on a model, and you wanted to be able to compare your scripts to scripts in other software really quickly, Lavaan is the exact right tool for the job. The general design of Lavaan has to accommodate those priorities. So the key thing that I found initially baffling about Lavaan is that when you specify a model, you're specifying really just a string. It's between two quotes. You make a quote mark, and then you specify your whole model, and then you close your quote mark. Single quote, double quote, doesn't matter. But your model sort of lives in this sort of quoted string. Then you fit the model with one of several different options. These are really just wrappers around doing the same thing. That there's a function in Lavaan called Lavaan. There's a function in Lavaan called SEM. There's another function called CFA, another function called growth. And these are just different sets of conventions that it will use to fill in the details of your model. They basically have different defaults about how much typing is going to be required of you versus how much the program is going to fill in for you. The Lavaan function mostly will just do whatever you tell it to do and will not add very much, if anything, to your model. The SEM function will add a fair number of paths. It's like medium number of paths. That's really the number of paths and the kinds of things that you want if you're doing a pretty standard conventional structural equation model. If you're doing a conventional confirmatory factor analysis or CFA, it's easy to write that really, really quick in Lavaan because it's going to add a whole lot of things for you and sort of fill in a lot of the details. Once you fit that model with one of these functions, you look at the results with summary, coef, fit measures, ANOVA, and inspect. Probably 80 or 90% of what you're ever going to do in Lavaan is going to use the SEM or the CFA function and summary, and probably ANOVA. Like SEM, CFA, summary, and ANOVA is the vast majority of what you would likely do in Lavaan for all model fitting. The rest of it might be needed for certain special cases or certain kinds of special models. The general structure of what you write in Lavaan is this form of you have some variable A, you have some variable B, and you have some operator that goes in between them. A might be a latent variable, might be an observed variable, B might be a latent or observed variable, and the operator is one of these. So it's either an equal sign followed by a tilde sign, just a regular tilde sign, or it's two tilde signs. We'll see sort of a number of examples of this going forward. But one of these three is like the key thing is you've got A tilde B means one thing, A equal tilde B means a different thing, A double tilde B means the third thing. The equal tilde is what you would typically use for a factor loading. In fact, this is sort of an important point to understand about how Lavaan understands your model. If you say A equal tilde B, that is exactly how it figures out that A is a latent variable. Something on the left-hand side of equal tilde has to be a latent variable. And when you say A equal tilde B, it means that you have a regression path going from A to B. When you have just the tilde, it's a regression path going the opposite direction. And it doesn't tell you anything about which variables are observed and which variables are latent. If you had A double tilde B, it just means there's a covariance between those. And again, just like those double-headed arrows that might be a variable going to itself, you can have A double tilde A. You can have the same variable on the left and the right-hand side of that double tilde, the same way that you'd have a double-headed arrow coming back to itself. In general, you write lines of this structure: variable, operator, variable. Each one of those lines corresponds to a path that you're drawing in a diagram. There's some quick ways to draw multiple paths at once, but in general, each one of those lines can correspond to a path in a diagram. Variable, operator, variable. In general, what each one of those lines does is it creates an element in a matrix. So again, we have this mapping between a diagram, the code that you write, and a matrix that gets written underneath behind the scenes. Lavaan uses these matrices. So although this second letter looks like a B to you and me, it's actually Greek beta. So it's lambda, beta, theta, psi, alpha, and nu. These are the matrices that Lavaan will create behind the scenes when you're doing things. All those paths that have equal tilde in them, those are factor loadings. They go in the lambda matrix. Those paths that have a single tilde in them, they go into the beta matrix. Technically, that's all for latent variables, but I'm going to sort of like hand wave around that. Variances and covariances among the observed variables go in theta. Variances and covariances among the latent variables go in psi. Means or intercepts go into for the latent variables go in alpha, and for observed variables go in nu. This is where we start getting into the equation form of a structural equation model. So these first two equations is how we would typically write a structural equation model. For mostly historical reasons, the convention is to use a lot of Greek for this. So we have the Greek letter eta is equal to alpha plus beta times eta plus little psi. Again, by convention, capital Greek letters are matrices, lowercase Greek letters are vectors. This first equation is sometimes called the structural model of a structural equation model. The second equation is sometimes called the measurement model of a structural equation model. The measurement model because it tells how the latent variables map onto the observed variables. The first equation shows how the latent variables relate to each other. So if you're drawing paths between latent variables, relationships between latent variables, those things go in the first equation. And if you're relating latent variables to observed variables, those go in the second equation. At the business end of a structural equation model, what we're really doing is modeling the mean and the covariance of our observed variables. We can talk about all these latent variables. We can talk about regressions. We can talk about all these factor loadings. We can talk about all these things, but what we're really doing is we're making a model of the mean and covariance of our observed variables y. So you have some set of variables y, and what all these equations and all these paths sort of amount to and reduce to is we have a prediction for the observed means, we have a prediction for the observed covariances, variances and covariances of our outcome. I've got equations here written out for them, mostly just to show you where the pieces all sort of fit together. I'm not sort of going to go into a lot of detail about each one of those things, but you can see that the observed variable means and the latent variable means impact the means of the observed variables. Similarly, you look at how the latent variable means impact the observed. It's sort of through the factor loadings and through the regressions among the latent variables. The exact way that it goes through there, we can sort of hand wave around and go over some details on if there are questions about that specifically. I'm happy to address that. For the covariances, we have this residual part of the covariances, theta, that maps directly into our observed variable covariances. But latent variable covariances and the regressions between the latent variables sort of have to get mapped through these factor loadings before they can have an impact on the observed variable variances and covariances. Again, I'm showing these equations to just sort of give you a sense of what's being created kind of behind the scenes, and we'll sort of use some of that behind the scenes information a little bit in some of the practical part in the exercises there. Let's see. In general, a model is this container for all these different paths. So you might have a bunch of different paths as specified by different lines. You put them all together into a model, and that creates the whole collective model together. Are there any questions about any aspect that we've covered so far? Hearing none so far. Okay. So now to get a little bit more practical. So if we were to make a regression path from a latent variable G to an observed variable X in Lavaan, so it's showing this crosswalk here between these two, between these three different programs. For anyone who might be familiar with M plus, that's G by X. The by in M plus is for measured by. In Lavaan, the sort of one-to-one correspondence is this equal tilde. That's specifically for latent variables on the left, observed variables on the right. If you have, in general, any variables at all, then you use a single tilde for those kinds of regression coefficients. Key thing is the difference between the equal tilde and the single tilde is not just latent versus observed and sort of what's permissible there, but the direction reverses. So G equal tilde X is going from G to X. Y tilde X is going from X to Y. It's going the opposite direction. That's a key thing to not mess up in your models when you're making them. You want to make sure that the directions go in the way that you're thinking they go. The mnemonic for this is the tilde is exactly like the regular regression in the rest of R. You can have Y tilde X and W and Z all together as a regression with a single outcome variable on the left. So the tilde is sort of the conventional direction of regression. The double tilde here, X double tilde Y, again, that's sort of covariance. And then Lavaan has this reserved 1 value that will be what you need for modeling means. Showing a crosswalk here to another software program tends to involve a lot more typing called OpenMX. It's another open source R package for doing structural equation modeling. The way that OpenMX specifies things is very much based on exactly the paths, regardless of what content they have. So there's one function, MX path, and you just tell it where things go from, where they go to, and if it's a one-headed arrow or a two-headed arrow. So you create all these different kinds of paths with the same function that just gives you a from and a to, and if it's one-headed or two-headed. And if you don't give all the names of the arguments, you get a lot less typing in there. But I don't think I mentioned much about the M plus syntax here in case people are familiar with that, but M plus uses key reserved words by, on, and with. And then for means, it uses these square brackets. So G by X is that measured by, Y on X is regressed on, and X with Y is covaries with. A key thing that you'll do in models going forward with Lavaan is sort of combine multiple paths into a single line. You can do it sort of on the left-hand side and on the right-hand side, but it's a little bit easier to think about, I think, if you combine multiple paths just on the right-hand side for the most part. So you can write G equal tilde X1, then on a new line, G equal tilde X2, G equal tilde X3, equal tilde X4, and 5, and 6, and 7, and 8, and 9, and write all those paths out. And that will be equivalent to writing this one line, G equal tilde X1 plus X2 plus X3 plus X4, and on and on and on. That writing out every single one of those paths on a new line is equivalent to this adding things together version. This will save you a lot of time, a lot of lines of code, and makes your code a little bit more readable when you write them out in this sort of added up way. Any questions so far? I'm not sure if I'm totally undershooting or totally overshooting right here. I guess Yes, there's a question. Hand up, hand raised.
Yeah. So this is very clear, but from the slide earlier when you were talking about mean of X, can you give us an example of when that would be used? Because the other ideas are very clear, but I'm failing to see when we would see like a mean of X being done in an SEM. If you can give an example.
So when would you have, so in general, all your variables have means. So the same way that they have variances and covariances, they have means as well. You usually wouldn't just have the mean of a variable sort of on its own. That's sort of not the most meaningful sort of setting for a model. But one, let me sort of jump back a few slides. Diagram that doesn't have means in it, but really could and could make some meaningful things in here. Thinking about this longitudinal factor model. Here, a subtle thing you may or may not have picked up on is that lambda x, lambda y, lambda z is the same at time 1 and at time 2. So that's a version of measurement invariance. We also actually have psi x, psi y, psi z, so the residuals are the same at time 1 and time 2 as well. So we actually have equal factor loadings and equal residual variances across time. So we have a kind of measurement invariance happening here. When we have that, what we can do with the means in this model is we can set the observed variable means at time 1 and time 2 to be the same, and then fix the factor mean at time 1 to be 0, and then estimate the factor mean at time 2 to be whatever it's going to be. And what this does is it lets us look at changes in our factor over time. So if we constrain the first time mean to be 0, and then we can see, did the factor mean go up? Did it go down? We might have real research questions and hypotheses about how this factor changes over time. So when we add means to this model, we add the ability to evaluate that research question of, does the factor mean change over time? And similarly for other kinds of models where you might have questions about the mean of one group versus another group. So you could have sort of multiple sort of categorical variables where you have different groups in your data set and you want to assess the mean changes over time for one group versus another group. In a setting that I've been working with lately, we have adoptive siblings and biological siblings, and we want to know, do the means and variances differ from one set of siblings to the other set of siblings? So we can assess those sorts of questions in this multivariate SEM context as well. Does that answer your question?
Yeah, it makes sense now. Why would we use that instead of like the actual variable?
Sure.
Okay.
Michael,
Other
I have
questions?
a related question.
Please, yeah.
So in regression, you could have, so usually you have an intercept, but you could have fit a model without the intercept, right?
Yep.
And in the same
We can
way
constrain
here,
that intercept to 0.
yes. So in the same way here, by default, I imagine you estimate a mean, but you can set it to 0 if you want.
Yep, exactly. Yep. Okay. So let's see. We're about an hour in, a little bit over an hour in. This is our first exercise. So I want you to write paths, that is, write Lavaan syntax that goes with this diagram. It has 1, 2, 3, 4 different paths on it. So your syntax should have 4 lines. There are 3 variables, and there's the constant and 2 variables, x and g. And this is the time to either like get out a script and really do it, or get out a pen and paper and really do it. That you will get very little benefit from sort of looking at it and going, yeah, I think I get it. And you'll get a lot more benefit out of actually going through the process. And it's like raise a hand, I think, in the chat once you think you've got it. If you want, I can put up, I don't think I can show two slides at once. But this is the key that shows you how the paths get made. Pause on this for a second. And then I'll switch back to the one that shows you the diagram that I want you to make paths for.
Are you able to switch it back to the previous screen? I can take a picture before you
Sure.
switch it back. Sorry.
No,
Thank you. All right, I got it. Thank you so much.
mm-hmm. See something in the chat here. Oh, don't give away the answers.
No. These are just the questions in your just so that
Oh,
people have the syntax.
okay. Yeah, you're right. Again, when you feel like you've got it, just like raise your hand. I think that'll be how I know if like 20 hands are up, then I think we'll know that we've got it. So I don't see hands going up. Are there questions? Do people have it? Okay, there's one hand up. Okay. Okay, does anyone want more time on this one? We've got 5 hands up. I imagine some people are just not gonna do it. Let me see if I can switch to this other screen. So we're going to be going back and forth a little bit between screen here. Is this probably just judging that it looks a little bit small still? I think that's sort of reasonable size. So my solution, I've got a couple different versions of this, but in a very literal way, the exact translation would be G tilde 1, so G has a mean. X tilde 1, so X has a mean. X tilde G, which is that G predicts X. Oops. You could also do that. Let's see. What am I going back to? You could also do this one as G equal tilde X. Doing it as G equal tilde X is probably a better idea because it emphasizes that G is a latent variable predicting X. And then X has a variance X double tilde X. I think I would even change my solution upon further consideration and do it this way, that this would be the final solution that I would have for it. 4 paths, 4 lines of code. One-to-one mapping between those paths that you write and the diagram that's drawn there. If you want, you can rely a little bit on multiple regression paths at once. If you had this as a regression path before, it could do it that way as well. So if you wanted to have a mean and a predictor on something, you could have the mean here and the predictor on something. What we can see later, though, is to a large extent, we'll write this one backwards the other way, actually. In Lavaan's helper functions, we can sort of go back and forth and verify it and see what it would do. But if we just wrote this one path that G equal tilde X, and then set other arguments to say, add means to things. And if we used either CFA or SEM, it would add variances to any variable that we have and do it in a particular way. Then it would, just this one line would actually create a model that had these other lines in it as well. So those sort of default behavior of Lavaan is to add paths to a model, even though you didn't actually draw them yourself. So you might be able to get away with writing just this one line and getting the full diagram, the full set of paths that you want in your mind. Any questions about that?
I have a naive question, Michael.
Please,
So here
absolutely.
the latent variable G doesn't seem to have a variability, right?
Right.
At least the first.
I didn't draw it anyway.
Yeah. So, but I imagine if we use the confirmatory factor analysis command or the SCM command, it automatically calculates a variance for that. Is that correct? Okay.
Yeah. So then a follow-up to that might be, what if I was doing something that I knew what I was doing and I wanted to do something crazy? I wanted to say G shouldn't have a variance to it.
Yeah.
Well, then I can say
G, yeah.
G refers to, so this would refer to the variance of G. And if I want to fix it to 0, I do this. I say 0 times that thing. And now the variance of G I've set to be 0. And this is sort of another important aspect of structural equation modeling diagrams. Any path that's not drawn can be considered a path that is drawn but has a fixed value of 0. I'm going to say that again. any path that is not drawn is the same as a path that is drawn, has a fixed value of 0.
Mm-hmm.
If I wanted, instead of fixing this value to 0, but I wanted to fix it to pi, and so on, I could write out whatever number I want there, and I would fix that variance of g to whatever that number is. Typically, we'd be fixing things to 0 or 1, or really just 0 or 1 for the most part. But any constant numeric value can be put in there and used as that fixed value. So I'm going to switch back to presentation. All right, so that was exercise 1. Exercise 2 is we want to draw a diagram that goes with this set of syntax lines. It's 3 lines, so there should be 3 paths that you draw. There's 2 variables. One variable is called Mike, the other one's called Brad. It has a 1 here, so that has a mean. There's a triangle somewhere in it. And these character values that I'm putting here, M, V, and R, those are the labels that go on the path coefficients. All right. So your task is to draw the diagram that goes with this set of code. And let's see, instead of doing the hand up, I think the thumbs up stays up. So do a thumbs up when you feel like you've got it.
I think
do
it's
a hand.
around.
Okay. Yeah. So
The thumbs up just
it
goes
away.
Yeah.
Goes away. All right. Then do a hand up if you've got, once you feel like you have the solution. Okay, I feel we've got 7 hands up so far. I'm just sort of assuming that maybe not everyone's playing along at home. 8? Oh, okay, maybe more people are. Okay. So we've got 9 hands up. I'm gonna probably call it at that. So diagram that goes with this model, one version of it could look like this. Again, your version might look different because you've arranged things differently. The key thing is not the particular way that it looks, but what's connected to what. So there should be 3 paths, a path from 1 to Mike, and the label on that path should be M. There should be another path that has 2-headed arrows that goes from Mike to Mike, and the label on that should be V. And the third path should be from Mike to Brad. And the label on that path should be R. And the way I've written this here, you actually have no way of telling if Mike or Brad should be squares or circles. The way I've written it over here, there's no way of knowing.
So, quick question.
Yeah.
So just a reiteration. So the arrow
Yes.
from Mike to Brad, does it matter which direction that arrow is pointing?
Yes.
It does.
Yes.
And which part of it tells us that direction from Mike to Brad?
The fact that Brad is on the left means that it's going to Brad.
Okay. Okay. Thank you.
Mm-hmm. So like this line here, this third line, Brad tilde R times Mike. That means that Brad is like the outcome of a regression. And you could have, so Brad is the outcome of a regression. The way you'd write regression in R, you'd have Brad tilde and then all the predictors of Brad. And here we just happen to have one predictor and it's Mike. So that means that we've got an arrow going from Mike to Brad and not the reverse. And again, this diagram shows Mike as manifest and Brad as latent, but this syntax actually doesn't tell you that. Lavaan would have to figure out, based on the data set that you gave it, which one of those variables are latent and which ones are in your data set.
So even if we don't have the equal sign, it would just consider that as like it'll figure it out as Brad to be latent depending on
So this is a little bit getting into like the psychology of like Lavaan and its development.
Sorry.
Yeah. So like my recollection and understanding of Lavaan is that it will consider everything manifest unless it's on the left-hand side of an equal tilde sign. So if, for example, I gave you this syntax and I intended in my mind for Brad to be latent, the way it's drawn here, and Brad was not the name of a column in my data set that I used for this, Lavaan would throw me an error. And it would say, variable Brad is not found. Because it would assume that anything that hasn't been explicitly defined as latent, being explicitly defined as latent by being on the left-hand side of an equal tilde sign, anything that doesn't have that must be manifest. So then it's going to look for it in the data set and it's going to throw an error when it's not there in the data set.
Mm-hmm.
You could get into trouble if you happened to name a latent variable in your model by the same name as a variable that's in your data set. Because then you wouldn't get that error, but it would still be a problem.
So if we really want Brad to be a latent variable here, I would say Mike equals tilde R times Brad. Oh, but R would be a different notation, I guess, right? Because
if I really wanted Brad to be latent,
yes,
I would need to have Brad be on the left-hand side of a tilde sign. So I'd need to have Brad equal tilde, but there's no way to actually do that. There's nothing for it to be there. So I actually can't even write that model in Lavaan.
Okay.
Which is okay, because I also can't fit this model to data.
Mm-hmm.
There's no way to actually fit this model to data. So I'm okay with it not being specifiable in Lavaan. I can draw the diagram, but it's sort of not a valid diagram in some ways. Other
Is the
questions
diagram
about this?
open? Yeah,
Go ahead,
I have
please.
one question. Is
Please.
the diagram open because you're not looking for the mean of Brad? Like it's not closed?
I don't know what you mean by open and closed. Could you elaborate?
Okay, so there's no arrow going from the one to Brad, but the one is represents the mean. So because
Yeah.
you're not looking for the mean of Brad, there's no arrow to go from the
Yeah.
1 to Brad. Okay.
Yeah. I have not drawn this path from 1 to Brad in the diagram, so I don't want the mean of Brad. Another way to think
Okay.
about that is I've set the mean of Brad to be 0
Mm, okay.
because I've drawn this path here, but fixed it to 0, which is the same as not drawing it.
Oh, okay. Thank you.
Mm-hmm. Very good question so far. Any others before we try the next one? Okay. So now we're going to do something a little bit different. We're going to see how this goes. We're going to write a matrix that goes with this diagram. Recall that a matrix has 1 row for every variable, 1 column for every variable, and the entries go from the element in the column to the element in the row. So this matrix that you're going to write for this diagram will have 3 rows and 3 columns. And some of the elements in that matrix are going to be 0, and some of them are going to be filled in by these numbers. Let me know, like, I think you can just speak up. Feel free to speak up if you have any questions about that, and raise your hand when you think you've got a solution.
I have a question, Michael, and it
Yeah,
totally is possible that I might have missed this during your explanations.
sure.
So we're not looking at a variance covariance matrix, right? We're looking at
Correct.
the coefficient matrix. And because
Mm-hmm.
the relationship is directional, does it matter that we are looking at rows to columns or columns to rows? So for example, I have XYZ, XYZ. Which coefficient? I guess my question is,
Where does it go?
yeah, exactly.
Yeah, goes
It's totally
from,
possible that I missed
yeah.
it, but
So it goes from an element in the column to the element in the row. So if you had
got it.
XYZ and XYZ, so XYZ going down, XYZ
Uh-huh.
going across, and you want a path that goes from X to Z, then it goes in the X column and the Z row. So it'd be in the first column, the third row would be that path of 0.6.
Yes.
I've given you half the answer.
Sorry.
No,
I
that's
guess
good.
not yet because you still
Yeah,
I think still the I don't know, but I feel like still the diagonal is a little mystery. So,
yeah. If you had, so the diagonals
but
would be,
wait. So let people work on
sure.
it. Otherwise, I feel like it's unfair.
Okay, okay. Again, hand up when you think you've got your solution. I guess you could also put a hand up if you've totally given up. And you just want to move on and like, I need help. I just want to see the solution now. There's a question in the chat that says, how do we know the matrix should be 3 by 3? So we know that the matrix should be 3 rows and 3 columns because we have 3 observed variables. Really, we have 3 total variables that we're modeling relationships between. So whatever relationships we want to model between, we need a spot for them to come from and a spot for them to go to. So we need as many rows and columns as there are variables. So here we've got X, Y, Z. We've got 3 observed variables. And we want to be able to model things that go from or to any of those. So we set that up in a matrix that has X, Y, Z rows, X, Y, Z columns, and they go from and to all of those. I think I'm going to switch my screen share over to this guy. So I've written this out as a matrix here in R. You don't have to do it in R if you wanted, but I have a matrix that has dimension names XYZ and XYZ, has XYZ across the top here, and X, Y, Z across the rows. I have an element that goes from X to Z, and its value is 0.6. It goes from the column to the row at 0.6. And then the other one goes from Z to Y, and its value is minus 0.3. So it goes from Z to Y, and it goes in the correct column, then row of that matrix. So this is the matrix that you should have created, this 3 by 3 matrix like this. Let's see. You might sort of wonder about why. So like, okay, by convention, I've told you that you go from a column to a row. Let me shift this share back to here. So why do we do that? Why do we go from a column to a row? It goes back to these equations that we've set up. In equation 1, we have, think about eta as a column of variable values, alpha as a column of means, beta as a matrix of regression coefficients, and then eta as that column of latent variable values again. So because we're multiplying this matrix beta on the right-hand side by this column of latent variables. When you do matrix vector multiplication with a matrix on the left and a vector on the right and multiply that through, it means things go from the columns to the rows, that the inputs come in on the columns and the outputs go on across the different rows. So if we had set all of these matrices up such that we had a column on the left and a matrix on the right, then everything would go row to column. But we've set things up to be the matrix on the left and the column on the right, so everything goes from column to row. In some areas of mathematical modeling, particularly with things that are called like hidden Markov models, which are another kind of latent variable model, they do typically have them reversed. So then you do have to go from row to column in those situations. Is there a question with that hand raised, or is that still up from the exercise? Okay, still up from the exercise because it just went down. Okay, so we've done this as a matrix now.
Mike, before you move on, I have a question about that. So
Yeah.
the diagonal, the zeros, if you put
Yes.
ones there, that means that you're estimating the means, right? Is it? Yeah. Oh, no. No.
No.
No. Yeah. No.
So
Because then,
the ones, if we kind of go back to our equations here, the ones go in here in alpha, or they go in here in nu.
correct. Oh,
So-
we are writing the betas and lambdas.
Yes.
Gotcha,
So we're
gotcha.
writing basically betas and lambdas. So we essentially never, ever, ever put anything on the diagonal of
Gotcha.
those regression matrices.
Got it.
So it doesn't make sense to regress a variable on itself unless it's the same variable over time, like autoregression. But the way you do that is you have two different variables. One is at time t, the other one's at time t+1, and you do regression across time in those situations. It's never from a variable back to the same variable with a one-headed arrow.
Mm-hmm.
Good questions. So next one, we're going to do another matrix. Here we have F, G, and H. I've drawn them as latent variables, but your matrix will be the same. Here, key difference is we have two-headed arrows. So again, make a matrix that goes with this diagram and raise your hand when you feel like you're ready or you feel like you've given up. And just speak up if you have a question. We've got 7 hands up so far. Let's see. I think I'll wait a little bit longer and see if I can answer this other question on the way. Jessica asked in the chat, why wouldn't you take the opposite sign of the known association for the reverse? I'm not totally sure I understand this question. I think it has to do with the previous exercise. So let me hop back to that one. I think it might be about setting up this matrix such that, if you have a path that goes from X to Y, why would it not be in maybe the opposite sign if it went from Y to X? I think that might be it. So like if you're going from here I've got x to z and it's 0.6. Why is it not also having z going back to x at minus 0.6? That's something that you could test, that you could include in your model if you wanted, but in general, there's this not sort of how the associations necessarily go. So I think that's sort of how we might think about like maybe causal associations, that like, oh, if X has this positive effect on Z, then if we sort of go backwards, then Z would have this sort of reverse effect on X. It's interesting to think about that in terms of like the full covariance matrix. So again, sort of going back to our kind of matrix version of all this stuff, if we have a regression element in this, say, beta matrix, the total effect that it has on the covariance isn't just beta. It's this thing that has this, crazy I minus beta with a -1 on top of it, which if you're familiar with mathematics, this -1 is for a matrix inverse. And if you're super duper familiar with mathematics, you know that you can write this I minus beta inverse as I plus beta squared plus beta cubed plus beta to the fourth plus beta to the fifth. And eventually beta is going to be 0 or close enough to 0 when you have standard models. So this I minus beta inverse is sometimes called the total effects matrix, whereas beta would be called the direct effects matrix. It's the direct effect of one variable on another variable. But the total effect of all the variables sort of on all the other variables is given by this I minus beta inverse. And then to see how that maps onto the covariances, you sort of do this I minus beta inverse and you do it sort of in reverse direction. Oops. This reverse direction is this superscript T, where it flips things, it flips the rows and the columns of everything. So I think what you're thinking of is sort of like that total effect matrix and how it's going to impact the covariance matrix. But that beta matrix is really just the direct effects. It has implications for all these other things, but we're only drawing the path diagram for the direct implications of what we're doing. I think that might answer your question, but let me know if you have more about it. Okay. So we're back at exercise 4. We're writing a matrix that goes with these path coefficients with this diagram that I've drawn out here. I'm going to switch over again to my code script that has that. So you should have a matrix that looks like this. F, G, and H, it should be a 3x3 matrix. Should have F, G, and H. If you want to put them in a different order, you could. There's no necessary reason why you have to put F, G, and H in that order. But it should have zeros in most places. The G to G element should have an A in it. The F to H element should have a B in it. And the H to F element should have a B in it also. Key thing is this element needs to appear twice. It needs to appear once in what's called the upper triangle and once in the lower triangle. The math word for this sort of operation is symmetric, that it needs to be symmetric about the diagonal. If you sort of swap the rows and the columns, you need to have the same thing that you started with originally.
Okay, now I have a question again, Michael. I'm sorry. But
You're
wouldn't
good.
you have to have ones in the diagonal here because you have a covariance? So the variability of f otherwise is taken as zero
I,
here, right? So it'll be a constant. Sorry.
yeah. What I've drawn here doesn't have a one in those diagonals. So like there's a little bit
Oh,
of
okay.
a
I thought
and
it's
it
sort of
and it
hidden.
there's a little bit of a you know question, I guess, around like, well, like I drew a variance here for G, but I didn't draw them for F and H.
Correct. Yeah.
Maybe that's on purpose. And if I'm taking this diagram absolutely literally and I'm not adding anything to it, then you get the matrix that I showed before.
Yeah. Okay.
A more reasonable model of the world almost certainly is going to have some kind of variance for F and some kind of variance for H, but they're not in this diagram.
True.
Yeah. Okay. Next one in here. Again, I'm asking you to draw a matrix that goes with this set of relationships that I've drawn. It's all two-headed arrows. I also still have F and G and H. And again, put your hand, oh, let's see, there's something in the chat. The question in the chat is, what is G to G element A? What does that mean? Does it imply that A equals 1? It does not imply that A equals 1. It's for the variance of G. So it just means that the variable G has some variability, and we're going to call that by the letter A. This isn't the full diagram. You can't have a diagram of all latent variables. But if we had a diagram that connected all these things to observed variables and sort of went about as a kind of full model, then we could be estimating that variance of G to some numeric value based on how it relates to other parts of the data. We've got 4 hands up so far. We've got 7. That seems to be about our upper limit on most of these, where people are willing to put their hands up for this. So this one was a little bit of a trick question. It's actually the same matrix as the previous one. How many people, so everyone put your hands down or like shout out into the void here. How many people drew the same matrix? I'm just going to hope that you drew the same. Thumbs up, some thumbs up on drawing the same matrix. So this is what I was mentioning before about the diagram not caring about the arrangement of the variables. It only cares about what's connected to what. So in exercise 5, G has a two-headed arrow going from it to it back to itself. Same thing in exercise 4. And then there's a two-headed arrow that goes from F and H, and there's a two-headed arrow in exercise 5 that goes from F to H. It's the same diagram. It looks, even with 3 variables and only 2 paths, it looks really different. It looks like it's a different kind of thing that you're doing here, but it's really the exact same thing. So when you're looking at diagrams, try not to be fooled by how it's arranged and think about what is actually connected to what. If there's a hand up that still has a question, go ahead. But if not, you can put your hand down. Okay. Now we're getting close to something that's now pretty close to an actual model, believe it or not, as ugly as this one looks. So here I want to write a model that is write all the different paths, the Lavaan paths that you would write to specify this model. There's one latent variable, there's 4 observed variables, and there's 4 paths. So your syntax will have at most 4 lines to it. So I want you to write that model syntax, that Lavaan model syntax that goes with this diagram. And then put a hand up when you've got it. Okay, we've got our 7 hands up. I think that's approximately, plus or minus epsilon, our upper limit on hands. So I think we're ready to show a solution to this one. So this, if you wrote out with 4 lines, this is the lines that you would write. G predicts W, G predicts X, G predicts Y, G predicts Z. If you wanted to put those together, you could put them together into a briefer line and just say G predicts W, X, Y, and Z. Key thing in here, now we're getting like, this is really like a model that you could actually fit if you actually had data to it. And we'll talk about what that model is in a second. But these are the paths that you would add. A key thing in there is this operator needs to be the equal tilde, and it's very important what's on the left versus what's on the right of that. Because the thing on the left is that latent variable, the thing on the right is the observed variable when it's this equal tilde operator. Go back here. Are there any questions about this one?
When we write it in the Lavaan, would you recommend for us to do like all of it with plus or to layer it how like we've been trying? Is there an advantage to either method or it's the same thing?
Lavaan will treat it as the same thing. It's user preference. So it is very, very conventional, to switch back here. It is absolutely conventional for people to write code like this. So I think within your first couple of models that you ever run, you're going to start writing code like this. If you want to write it like this, you absolutely can, and Lavaan will treat it just the same. And you'll create the exact same model, and it will run it the same. It will work exactly as well as any other version of writing it. The two will create the same thing on the output. So it doesn't matter really that much what version you use. I have no particular recommendation other than make sure that Lavaan is doing the model that you want and not the model that was easy to write. So we're going to do one more exercise with this, and then I'm going to talk a little bit more about it. This one, I think, will be quick. So again, write the model in Lavaan syntax that goes with this model. Yeah, people are getting this one fast. Yep, we've reached our max of 7. Okay, why was this one so fast to be made? Because it's the same exact model as the previous one. Yeah, I'm up to my old tricks again. I made one that sort of looked complicated, and I made one that looked easy, and it's the same exact model. So do not be fooled by the diagram. If it looks crazy and it's laid out like this, it doesn't matter how it's laid out. It's really the same simple model that we had done before. Let's see, I see there's something in the chat here. So my plan on this, just to kind of overview, was actually to wrap up reasonably soon. I had this slotted for 2.5 hours, not 3, but however we want. If we wanted to take a break before we wrapped up, I'm fine either way. Okay, so now it's good. So we have here actually like a model that we could conceivably fit. All the things up to this point have been mostly sort of toy examples or things that like just to try and get your juices flowing, to try and get you thinking about the diagrams and the matrices and the syntax and getting you to sort of map between all these things. So to build those bridges between these sort of 3 ways of expressing a model. Now we're at something that we could actually fit. So we can go back into the code example that I have here. And I wrote this out in the syntax. So this was the model that we had before. G equal tilde W, X, Y, and Z. And I'm saying in here, well, I could just say that I want to do it as a CFA. So I'm now calling an actual Lavaan function on this actual Lavaan syntax. And now what I can do is call this function called inspect. Inspect is really good at seeing the underlying matrices and things that Lavaan has built. So when I say inspect what equals start, it means the starting values. We'll talk a little bit about that, but essentially in structural equation models, you have to put in some initial values for parameter estimates, and then it will try and improve those values, then it tries to improve those values and tries to improve those values until it can't get any better. But it has to start somewhere, and Lavaan will pick starting values for you that are usually pretty good. So this inspect thing returned a list. The first element of that list is called lambda. Lambda is the lambda that we had from the equations before. It's the lambda matrix that goes with this model. This lambda matrix has one column and 4 rows. The column is labeled G, and the rows are labeled W, X, Y, and Z. The elements here for starting values is, first one is 1, and then the other ones are set to 0.7. So this lambda, this is the factor loadings matrix. It's the matrix that maps the latent variables to the observed variables. This theta, now because I've used this CFA function, even though I didn't have some of these paths drawn, it added paths for me. This theta down here is the residual covariance matrix. What it did is it said each observed variable should have a variance. and we're going to start that variance estimation at 1. Additionally, it says the latent variable, g, should have a variance, and we're going to start that at 1 also. It says there's a set of intercepts, means for all the observed variables. It added a whole bunch of stuff that says those are 0. It says this intercept is 0. Critically, if I change this, oops, I got an error because Lavaan is not the thing. Lavaan is the thing. If I say do this as Lavaan, not as CFA, look here, it did not add variances for my observed variables. Those are all zeros now. There were ones before. It also did not add a variance for my latent variable. It's still 0. It was 1 before. So using the same syntax, this is a key thing to be sort of wary about and look out about with Lavaan. If you use a different function call, you'll get a different model even though you have the same syntax. So I put in the same syntax here, the same code, and I said ran it with Lavaan, and I got a different model than if I ran it with CFA. Depending on what model you want to fit, you might want to use the Lavaan function or the CFA function or the SEM function or any number of other functions that Lavaan could provide. It just depends on what you want it to do. Are there any questions so far? We're basically sort of starting to wrap up, so. What are good next steps to learn more? You're way ahead of me. Look at like further reading. So we'll get there. Just give me a minute. I'll come back to it. Okay. So there's the one last thing in this practical. I think we don't have to do it. You can do it as a bonus if you really want to. I want to give again some like a review and overview of like stuff that you're definitely going to use a lot in Lavaan if you use Lavaan, and sort of a summary of what those functions are. Okay, the Lavaan function, basic, create a model. It'll do what you want it to do for the most part. If you have like a crazy idea and you want Lavaan to sort of not add stuff that you didn't add, the Lavaan helper function is what you want to use. If you're doing something that looks a lot like a CFA and you want Lavaan to help you out and add paths that sort of make sense with a CFA, a confirmatory factor analysis, use the CFA function. If you're doing something that's a pretty conventional SEM and you want Lavaan to help you out by adding the typical conventional SEM stuff, use the SEM function. Similarly, if you're doing a growth model, like linear growth curve model, latent growth curve model, there's a growth function. Do that. A nice thing to quickly do exploratory factor analysis in Lavaan is this EFA function. Nice thing in particular about that EFA function is you can evaluate 1, 2, 3, 4, 5 factors all at once in one function call. It's pretty handy to do. Once you fit a model, the typical thing you do is look at summary, look at the parameter estimates, look at ANOVA, compare it to other models. So you might not just make one model, you might compare to multiple models, and you might look at fit. And again, sort of in a workshop like this, there's only so much time and only so many things that I'm going to sort of leave you with. But the goal of this workshop is really to give you a sense of this mapping between syntax and the diagram and the actual matrices and model that's being made. So hopefully you have a sense of how those things relate to each other and sort of have the tools to build models based on that. Some other things in Lavaan that might come up a fair amount. that I use often is this modification indices. Modification indices are saying like, well, I have this model and it doesn't fit all that well. What can I add to this model? And modification indices give you suggestions about things to add. When a critical thing with modification indices that I cannot emphasize enough, it's data-driven. So it has all the strengths and all the weaknesses of any kind of data-driven modeling approach. You should never, ever, 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 ever report data-driven modification index added parameters as if they were theory-driven. If they're data-driven, report it as data-driven. Report it as exploratory. Exploratory work has a great place to be in science, but just not pretending to be theory-driven. So data-driven is fine, but report it as data-driven. That's the key thing with modification indices. This lav test score function, if you have equality constraints across groups and you might consider removing some of those, that function is a nice way to think about removing those constraints. Looking at different ways of assessing fit, AIC, BIC, log likelihood, good things to look at. This update function is a key one too. Update lets you avoid copy pasting the same model syntax again and again and again when you're fitting a model and then a slight variation on that model and then a slight variation on that model and a slight variation on that model. Instead of copy pasting that syntax, which might get kind of long for a complicated model, use this update function. So that update function will save you a lot of headaches and errors in debugging, some crazy thing that went wrong with your model. We showed a slight use of this inspect function, so you can actually look at the model that was made. Another similar function is this par table function that sort of lets you get a sense for the different parameters in your model. Again, it's nice for evaluating constraints and things like that. A couple other things to look out for inside. These are arguments that go inside Lavaan functions, inside that CFA or SEM or Lavaan function call. This mean structure equals true, add means to a model. Standardized latent variables, std.lv equals true. So if you want to have like z-score latent variables, if you want to have uncorrelated latent variables, you can just say orthogonal equals true. Set all those things to not be correlated. This sort of goes in two categories as a useful argument and also a thing to really look out for. Lavaan's default behavior when you have missing data is listwise deletion. That is essentially the only unacceptable version of handling missing data that I think any program does, and that is Lavaan's default. If you want to do something smarter with missing data, and you definitely do, say missing equals ML or missing equals FIML, and that will handle missing data in a much, much, much smarter way. Some more things to look out for. In general, SEMs assume multivariate normality. This is how we're getting away with only modeling the mean and the covariance matrix for a data set. If it's multivariate normal, the only thing that there is to care about is the mean and the covariance matrix in a data set. In general, there's been a lot of research that says it doesn't really need to be multivariate normal. It just needs to be not too far from multivariate normal. The main things to look out for there are 1, skew, 2, binary data, or 3, heteroscedasticity. So I didn't write heteroscedasticity down there. As long as it's not too skewed, too long on one tail or the other tail, or you don't have binary data where it's really just two categories, or if you don't have like zero inflation, or if you don't have different variants for one end of the variable versus another end of the variable, it's sort of multivariate normal enough. That's the consensus of 50 years of simulation studies on SEM, that it's multivariate normal enough as long as it's not skewed, binary, zero inflated, heteroscedastic. I mentioned before this missing data handling, look out for that. I mentioned this in one of the examples, the CFA versus SEM versus Lavaan will give you different models based on the same syntax. The key thing is always to examine the output and make sure that you've got the model that you wanted to fit that matches the output. Something that we didn't talk about, but this is a very approachable article on by Bud McCallum and a few other people, is the problem of what are called equivalent models. I don't just mean models that are diagrams to look differently but are the same. You can actually have models that the diagrams are really different, where there are different paths going between variables, but it actually produces the same covariance matrix. The key one that comes up so often that is one of these equivalent models is a mediation model. If you have 3 variables and you've got x to m to y, and also the path that goes from x to m, m to y, and from x over to y, that typical 3 variable mediation model, that is equivalent to any other model that has those 3 paths. You can swap the direction of any of the one-headed arrows in that model. You can add 2-headed arrows instead of the one-headed arrows. You can do anything that you want with that model as long as it connects everything to everything else. And it's the same model. So you have this family of equivalent models for mediation. That means you're not really testing the fit of that model. It means you're testing the fit of that or one of its potentially infinite equivalent models. So look out for that. And again, this article by Bud McCallum is very readable about that topic. It's geared towards exactly the audience that anyone attending this workshop is. Last thing to look out for is something that came up pretty early on, is the diagrams that appear in papers are often in shorthand. So they don't include everything that you need to know to fit that model in the diagrams most of the time. So just look out for that and be prepared to have a bit of a learning curve in fitting models that way. There was a question in the chat about further reading. Here's my recommended bits of further reading. This one is an article by Yves Russell and Vidal. It's basically a tutorial that spans the technical bits of SEM with the non-technical bits of SEM. And so I think the subheading on this article is, where did the numbers come from? The idea is trying to get you to understand the full way that you go from inputs to a SEM program to the outputs that it's giving you. Where do those numbers, the results that it's showing you, where do all those things come from? If you want to know all the details of how that's done in a very minimally technical way that's very approachable, this article is how to do it. It's by Yves Russell. It's in the British Journal of Mathematical and Statistical Psychology. I'll put references here at the end. Very recently published. Other thing I'll point people to is Ken Boland's book. This is his 1989 classic book. It's on every respected methodologist's shelf. I've got my copy right here. Don't know if this shows up for you, but it is the classic book on structural equation modeling. Still basically the best book that you can get on it. If you're going to get one book and read one book on it, on structural equation modeling, that's the one. This is the paper I mentioned before, Michael Rantilla, about how normal is normal enough. Let's see something in the chat here. Is everyone having audio issues?
Did you move away from the microphone, Mike?
Just now?
I think I can hear you, but it sounds like you're talking from a background, like a distance. I don't know whether you moved away a little bit. Yeah.
No, I'm sitting at the same chair that I was a second ago.
Now it's better.
I think it's better. Yeah.
Better now. Okay.
Okay.
It's possible that it's not an audio problem. That's actually my voice going.
True enough, we have been talking for 2 hours.
Micah Rumtella, this article here, I definitely would recommend that. If you're doing longitudinal structural equation modeling specifically, Todd Little has a book on longitudinal SEM that I would highly, highly recommend. Something that comes up a fair amount in structural equation models that we didn't talk much about was called model identification. It's basically saying the basic idea of model identification is, can you actually get a unique set of answers for your model? Or are there infinitely many solutions to your model? A model that's identified will give you one best answer. A model that's not identified will sort of run off the rails and not work out for you. Particularly, identification issues come up with latent variables and latent variable models. And I have an article that addresses this, and I think the clearest way, and points to a lot of resources on it. There are actually tests that can determine if your model is identified, and it can point you to exactly where your model is not identified if it is not, and so point you to a solution. If you have ordered categorical data and you want to do growth models, this article by Paris Mehta is an excellent one that I would definitely recommend. It's about squeezing interval change out of ordinal variables. It's an absolutely excellent article. Okay. Last some bits here, sort of going forward. Some general advice about how to build models. So start smaller and simpler than your target model. If you want to fit, let's see, I think I've got this diagram here. If you want to fit this model, to each their own, if this is the model that you really want to fit, do not start by specifying out all that Lavaan syntax to get exactly this model. That is not the thing that you should start, because there's definitely going to be some mistake somewhere, either in the diagram or in your syntax or in the data set or something. There's going to be a problem and you're never going to be able to solve it. Start with the smallest, simplest model that you can possibly think of running and build slowly a more and more complicated model from that point. So start with a smaller, simpler model than your target model and build up to it. Small incremental steps that way. Once you've got a model that works, keep it working and just sort of build up from there. You want to check for and resolve any warnings that come up. A novice thing that I see people do a lot is they'll fit a model. Lavaan will be screaming about 8 different kinds of critical warnings, and people just go on interpreting the model anyway. Don't do that. Don't be that person. If it has warnings, try and resolve those warnings. Check the output. Make sure that the model in your head is the model that Lavaan fit. Sanity check parameter estimates. Create a family of similar models to evaluate similar kinds of theories similar kind of parallel explanations that could be going on, and do nested model comparisons or do non-nested model comparisons, but don't fit one and only one model as if that one's going to be the right one. Fit a bunch of models. Doesn't take long to do. Fit a bunch of models, compare similar models together, and evaluate those based on absolute and relative fit. Wrapping up now. So hopefully we have a sense of the big picture of what structural equation modeling is. We have an idea of how these models are diagrammed. We have an idea of how Lavaan is designed. We have an idea of how to translate between matrices and paths and diagrams and code and sort of map those things back and forth between each other. And going forward, you'll be able to learn that Lavaan can do some cool things. And this is just sort of your very, very basic starting point to give you more of a cognitive frame for this, more so than a bunch of scripts that just fit a bunch of models and we don't really know how the scripts work. The goal here is really to give you a foundational sense of what SEM is doing and to have you be able to build on it from there. Okay. That's it. I'll stick around if there are questions. I'm happy to answer more. And let me switch over to the slides here, so the references here, so that those show up. So these are the details on the references that were in there.
Well, thank you very much, Mike, for a very interactive workshop. So, excellent job.